factor to just see what is going on here. And ultimately, we've also been working on applying this neural network to perform quantum error correction. That's what is going to make quantum computers, say, useful, I guess. And in the long term, not the neural network we make, the quantum correction is its own field, and there are many, many different techniques. That's just the last toolbox. But this is still a bit of the road. It's not that complication where you can use data to do physics. And I think I can do that. Thank you.
Okay, thanks a lot, Giacomo, for your talk. Can we have a question?
This is a simple question for me. Is there quantum computers, or do we really have one here? I mean, not here, but...
Well, funny you say, because actually Santa Barbara, they're building currently, they're building one, and that's from the Google thing. So there are quantum computers, and I forgot to thank you for the question, because I wanted to say, but I forgot. There is this thing called IBM Q Experience, and I suggest you all to go and check it out. Then you can make an account, and you can literally run your algorithm on a real quantum computer. I'm not kidding. This is IBM Q Experience. You can run it for as long as you want, of course. You have tokens, and you can just build some simple algorithm, design a circuit, and just play around with it. And that's the service that I use to do that little simulation that I showed you in the talk. I just register, I give some token into a circuit, and I simulate like a small quantum magnet using the circuit. Clearly, the simulation degrades very quickly, but it was still very interesting to do that. I guess it's here. Yeah, so that was the chip I used. The 5-qubit. Yeah, the talk is 170 megawatts, so every time I go from one to the other. 5-qubit, yeah. I simulated 5 quantum spins interacting, and this is the result. But again, it's noisy, so you can run a very long algorithm. It's very cool, right? Yeah.
You can go back to the second, just for me to get clarity, you can go back to the second last slide that you showed with the actual wave function on the left, and then the neural wave function. So the wave function on the left, that is really a photograph that was made from the lithium atoms?
No, so this is, sorry, maybe I made it clear.
Is there any connection between the instrument you had there and the lithium atoms?
No, the lithium atoms was the previous experiment. And that's what I was for the supervised learning part. And this is just 12 electrons, and that's just a simulated data. So this was, those really electrons were like quantum spins, and which is the same property, but I didn't commute Pauli exclusion principle there. They were in different space, and they were moving like a spin chain. And this was like a time evolution of the spin chain. And this was after some time that the system was evolved, and I took the wave function there. But it's not related to the lithium atoms. Yeah, just a synthetic experiment.
More questions? Yeah. So I wanted to ask a question about bias. In the example that you gave, it's clear that the wave functions are only up-down. But in the case where you don't know what the wave function, what your solution might look like, how do you know that you're not introducing bias? Because if you put in Gaussians, then you're going to get out Gaussians. It's like classic. You're looking for hammers.
That's a very good question. Thanks. Yeah, so that's true. But that's why we're physicists too, right? We have some insights on what the physics is, and we are not just saying like, okay, this is an algorithm, and it's just gonna look for all possible solutions. We input some knowledge that we have on the physics that we want to explore, and so yes, that in some sense that introduces bias, but we always hope it's a good kind of bias.
Just a clarification question. So you created a reliable neural network to which you can feed a wave function, and it will tell you what the wave function is. So how are you going to use that? So you would actually, am I mixing up stuff? So you can take the picture from the lithium-ion experiment and feed it into this neural network. Is that what you want to do at the end?
Yes, and that's what we are currently doing, not for the lithium, for another experiment. But yes, we feed the measurement of the single atoms, so that's not the wave function directly, but the wave function is some hidden structure underlying this data. And we use a neural network to extract this wave function. And there are many reasons why we want to do that. And one just on top of my head is that we can measure things that are not accessible in the laboratory. Say, like quantum entanglement is one example. That's a very, very hard thing to measure in the lab. It's a very non-local property. That's being measured in an experiment. It was like very, very philosophical. It was very complicated, and it's not possible to scale to a large system. So, but if you know the wave function, then you can compute things such as entanglement, for example. So that's one reason to extract information that are not accessible in the original experiment.
Giacomo, I think one of the last calculations you showed, you were pretty proud of the fact you did 150 electrons.
Yeah, they were like quantum spins.
Spins. And you got a wave function, right? So where did you put it?
In a neural network. It wasn't the thing that made it. It's essentially, I have to wait a moment. It's essentially what happened here. So it was an Ising model. It was like a simple quantum spin system, and we performed measurement of the direction of the spins, creating a data set, and then we trained the neural network and doing unsupervised learning. And by the end of the training, the neural network itself was the wave function.
But I thought like 2 to the 150 required all the shipping containers.
Yeah, it does. But we don't store the full state.
That's what I asked.
Here it was just a demonstration. So this is 12. Let me see. This is a demonstration just to show. Yeah, but the principle is the same. Even in this case, I just printed the full wave function.
Any of those could be the numbers you want. Like if you challenge it.
Well, that's what so I can compute the wave function for any of those states because I have an explicit representation.
Yes.
So I can always do a big loop and ask the neural network to tell me what's the wave function for each state. And here I did the same, and I finish all the states in a reasonable time, but I cannot do it for the 150 spins. So in that case, I can produce the wave function, but I can produce observables, say.
Right. Okay. So in principle, if you sort of waited long enough and computed long enough, you could publish all the numbers. They are all there, but you're not printing them out. Yeah.
Yes, I still don't know the normalization of the
you have a scaling problem where you can only simulate up to a certain size, and that would be how you would get the data to train in the first place. So then if you go carry it over to, if the purpose is to go over carry an experiment that's bigger than you can even simulate on the computer to see what it's doing, but how would you get the data? Or if it was data for a thing you could scale, then why do you need the experiment? You know,
well, the experiment can always generate the data, right?
Yeah, that part, yeah.
So even if it's a larger system than what you can simulate in the first place, I mean, that's the point. That's maybe I should have made this clear, is that we want to be in the regime where we cannot generate the data ourselves. We want to be in the regime that the experiment can realize that, can find this wave function because they have this platform, and we can use this technique to extract this wave function from the data. And that's the regime that they can always generate data. You can always if you have like
you can always measure the experiment.
You can always measure, because what we use are very simple, like just occupation number or spin magnetization. This is always thing that when you have this single atom control that you can achieve, right? And yes, that's it. Yeah.
Oh, I see. So this unsupervised one, you don't need the training data, right? Like, I mean, you don't need the synthetic training data. I mean, for the test you did, but for the experiment you could just do it straight away, I guess, right?
For the experiment, yeah, that's what we're doing right now. They run an experiment, and it's a different type of platform. It's not lithium atom, but rubidium atoms. They're trapped with optical tweezers, and they can measure their excited state or ground state. They gave us the data, and we found the wave function.
That's really cool.
Yeah.
Okay, great. Okay, we still have a little bit of time for more questions. If there are any. Yeah.
What is it that makes those? Why do the waveforms make that pattern of reducing squares? Is it something about the lithium itself?
Excuse me,
Why do they make those patterns?
Yeah, that's a good question. This is like it's just the way that I plotted it. It was totally accidental. So it's just that there is. So that's a good question, because you can see the structure that is in the wave function, and it makes this square just because I think by chance this wave function had this structure particularly. But that's one of the points I was saying, that you don't need this like exponentially large number of parameters because you exploit some structure that is present, and this structure you can clearly see here. Yeah.
Was it a ferromagnet?
This was for the expert here. This was like a quantum quench, the time evolution of the long range quantum ferromagnet. Yeah.
I thought I saw some ferromagnetic points somewhere. Great. Okay, one more question, or one or two more questions.
It seemed from the graph where you had the two theories and you had the assignment using the neural network, and then there came the point where it really wasn't sure, it didn't have a lot of confidence. So that's a reasonable conclusion be neither one is really explaining what's going on, and then if that's the case, would this unsupervised learning be able to provide you with some new theory that you could then go test, or are you kind of back to the drawing board with like what's really going on?
Yeah, that's a great point. So this did exactly that. So this tells you that the network associates high probability to this theory, but they're very close to each other. So in this regime, you cannot definitively tell which one is correct. But if we ran unsupervised learning on this data, which we did not, and but I hope this is going to be the case soon enough, then again you could, instead of just validating a theory, you could extract the wave function of the data, right? So, and of course it carries all experimental imperfections, and you need to take that into account. Your reconstruction can only be as good as the data. So, but yeah, that's a very good point.
Okay, one more question. Great.
I think maybe it was more than that. Forward. Yeah, right here. So on this one, the different colors, what are those? I know you said that those represented in terms of a certain number, and I'm assuming you chose the scale in terms of like if yellow meant a certain number, red a certain number, hot, cold, whatever. Could you just, I'm just thinking, kind of related back to some of the coding we talked about this morning, and to realize that with a picture, you can represent 4,096 different coefficients, and that you've got the color that represents, I think from what you said, that the color goes with the number for the coefficient. Is that what you said?
Yeah, that's correct. Yeah, that's true, but maybe I should be more clear about this. This is not the type of data that we feed into the network. This is the wave function, and we feed measurements performed on this type of wave function. But if you, I'm just asking, maybe they're coefficient, but this is, maybe I didn't understand the question correctly, but if you meant that these are the type of, like the pixel in the image that we feed, no, it wasn't that.
It's taking the data to produce the pixel.
Yes, it's taking the data to reconstruct these colors, essentially. Yeah.
So the blue might represent like...
Yeah, so in this case, actually, those numbers go from 0 to 2 pi. They're like a kind of, so it's just like a color, essentially, yeah, and you have free to choose that. Yeah.
Kind of like these are like the probabilities to generate different data that you would feed in, right? Like the colors would be like places you generate.
Those are different kinds of figures, essentially.
Okay, yeah. Okay, thanks for all the great questions. That's really awesome. Yeah, thanks a lot. Okay, ready to try.
So please put this on your belt. Put it in your pocket.
Yeah, that was great. Yeah, let's take 2%. Thanks so much.
Put it on. I'm trying to just hold it.
Hi, my name's Sherry Harper, and I work with this group called Contemporary Physics Education Project, and we basically do lessons and posters and so on with some contemporary topics in physics. And we have a teachers contest for people who do some of these topics, like nuclear physics and particle physics and so on, in their classroom. And there are a few papers out when you're dropping off your survey. And also, I believe they tweeted an announcement about it. The deadline for it, unfortunately, is March 1st, so it's coming up. But there is a small monetary prize along with some of our materials from the Contemporary Physics Education Project. So if anybody's interested, if you want to go to our website, it's www.cpepphysics.org, and there's information about it on there also, so cpepphysics.org, and there's some information regarding that.
Okay, welcome back for the afternoon session of the Automating Insight Teachers Conference. I hope you all enjoyed the morning session and a good lunch. So the idea of the afternoon speakers, so the first two speakers gave us kind of a broader introduction to so kind of like philosophy of machine learning, kind of what it is, how it's kind of helping science in a bigger picture, and then we saw this one example of helping with electronic structure, and then Lauren went into great detail about how one of these machine learning models work, and I just thought I'd mention, I think Yasmin mentioned as well, that that's really how these models, many of them do work, that are like the state of the art. That same story with these weights and biases and neurons, that's not like a cartoon of a model, it's really kind of how they actually look, just with some extra layers or a few more neurons. So tying into that, our next speaker is Yasmin Bari, and she currently works at Google, but has a physics background. She got her physics PhD from Berkeley a year or two ago, and then she did a residency at Google Brain, and now she's a full-time research scientist at Google Brain, so it's a pleasure to have her. And she's going to be telling us more about the kind of state-of-the-art style of the kind of thing that Lauren told us about with neural networks. So, yes.
Thank you, Miles, for the introduction. So I hope that through the talking, I can give you a sense of what the frontiers of deep learning research are like. A lot of my emphasis will just be on deep learning. Lauren gave a very nice introduction to some of these ideas, but that means that you have some network where you send in some inputs, and you have very many hidden layers that are doing some computations, which just involves doing some matrix multiplications of your input, followed by application of nonlinearities. And you do this over some number of layers. That's the depth of the network. That's the deep in the deep learning part. And so I'd like to give you a taste of what research at this frontier is kind of like, then also talk a little bit about my own work, and then snippets of research that other people work on. So please do stop me and ask questions, because I'm not sure quite if I got the level of this talk right, so do slow me down if something isn't clear. Just kind of as a global view of different types of learning, Lauren talked about machine learning and AI. That's one distinction between two different fields. Another way to kind of classify some things that come up in this field are these three different kinds of learning. There are also some other types, which I haven't listed here, but broadly speaking, there's three classes. One is supervised learning, so that's the kind that actually has had the most success in recent years with deep learning, and that's where the learning problem that you have consists of learning from functional relationship between inputs and outputs. So you have some training data that consists of inputs X and outputs Y, and there's some underlying functional relationship between the two, and you're just going to learn what that functional relationship is by looking at some finite number of samples. So that's what deep neural networks are really good at doing, and it's a problem it's an area we've made a lot of progress on. Unsupervised learning is when you don't have labels or answers for the actual problem. So let's say you just have inputs, you just have samples X, and you'd like to discover something about them. Maybe you'd like to understand the underlying structure that's there, but you don't really know what it is. One way you might do that is just try to plot some of your data and see if you can visually see some of that structure. But what makes this hard is that you don't know if the basis in which you took some of your measurements is actually the one in which you're going to observe the structure. So you kind of need to discover that. And this is a very open area. We haven't made as much progress on it. We don't really know what the right approach is. And then there's also reinforcement learning, which is more connected to things and ideas from control theory. But the setup there is usually that you have some agent that's interacting with the world, and because it's interacting with an environment, there's some uncertainty that's associated with that. So if the agent were in a perfectly closed system and you knew what all the consequences would be of the agent taking actions in this environment, then the problem would be closer to control theory and would be easier to solve. But the agent here in this setting is interacting with some environment that you don't really know, and so the agent wants to, for instance, do something optimal. So as the agent kind of explores around in its space, it receives some rewards for different kinds of actions that it may take, and then the agent wants to learn what is kind of the optimal sequence of actions it should take to obtain the best rewards. And so solving that problem, basically because you don't know, you can only get some rewards by actually doing this exploration kind of strategy. You have to learn by exploring, and that's kind of the domain of reinforcement learning. And Lauren already touched about some of the differences between machine learning and AI. So machine learning is more just making machines that do intelligent things, tasks that can kind of aid humans, and often draws very much from statistics and computer science, but it's a little bit more domain limited. So you specify the domain, and then maybe you can just use pattern recognition, for instance, to kind of do something intelligent. It doesn't have to be very human-like. But then the goals of artificial intelligence are to build some more general system that can maybe do lots of different tasks. And for this, the field draws from, it's very interdisciplinary and draws from other areas like cognitive science, neuroscience, and so on. Okay, so why is deep learning so popular now? It turns out that some of the basic primitives for deep neural networks have been around since the 90s. So for instance, one of the main types of networks that is very good for image classification, so let's say you have a training set consisting of images of cats and dogs, and you have these samples, and then you want to learn this functional relationship. So one type of network that does that very well, and I'll try to come back to say a little bit about what this primitive is a convolutional neural network. And it was actually first introduced in the 90s by Don LeCun, who was one of the pioneers of deep learning. And so at that time, people tested these methods, but they weren't really performing all that well, or in a very impressive manner necessarily. And then all of a sudden, this current wave of deep learning started around 2011, 2012. And this was one of the papers that really brought it back. It introduced an architecture called AlexNet, but actually the architecture itself, so this way of basically taking inputs, doing certain linear algebra computations, so matrix multiplications, passing them through nonlinearities and so on, through some number of layers, the sequential kind of processing from input to output. So this architecture, the primitives were really close to networks from the 90s, but nonetheless it resulted in very impressive performance. So this was kind of the breakthrough AlexNet result, and I took the abstract of the paper that had this breakthrough result just to give you a sense of the scale of the problem. So this is a network that was classifying 1.2 million images. The data set here is referred to as ImageNet. There are 1,000 different classes. The network is huge. It has 60 million parameters.